My talk will be a bit different in spirit. It will not be about localization, but I chose a topic which is of different spirit, of course, but it kind of shows also that in mathematics, things which are intuitive or sometimes natural require also some non-trivial tools. In these works that have been presented for the collaboration of Svetlana, for instance, geometric measure theory is a tool which plays a big role, but also in general, partial differential equations as well. And the topic I will present, besides having its own interest, also kind of combines the same philosophy. So the starting point of this story is a very simple model where you can consider, let's say, a metal wire. So think of a metal wire in three-dimensional space, or in higher dimension for what you want. And the goal is to find a surface here that is attached to the wire and which minimizes some energy. So in the simplest formulation, we can assume that this metal wire is a graph over a domain. So let's say I have a bottom domain here, omega, which is a subset of Rn. So this is my Rn. And then I have an extra variable R here. The metal wire, it's a graph over the boundary of the domain. So this metal wire is represented by some function f defined on the boundary omega with values in R. And what you want to do is to find a surface that is attached to the wire and, as I said, minimize some energy. And there are several models you can consider. A classical model comes from linear elasticity. And so if you do linear elasticity, you're going to minimize the elastic energy of a membrane attached to the wire. So this would be some integral over omega of grad u squared, let's say, over 2 by normalization. So what is U? U represents, so the graph of U represents this membrane, right? So graph of U is my elastic membrane. And so this graph is attached. So U on the boundary of omega is equal to F. Okay, so you minimize then Dirichlet energy with Dirichlet boundary conditions. So very classical problem in the calculus operation. Now, this would be the starting point, but it's a bit too easy. So the next thing you say is that, okay, I have my metal wire, but I have gravity acting on it. So when gravity acts, the membrane will tend to bend, okay, because of the weight. So let's add here a gravitational energy here. So U is my height function, right? So this is x, and this will be, let's say, the point on the membrane will be x U of x. So U of x is the height. So this will be now my new energy. Still kind of easy. So G is a constant, right? This is gravitational constant. I'm a mathematician, so G is 1. So I drop it, okay? So this is my energy still. I'm happy with that. But now I want to make it a bit more complicated. So this would be like, again, too easy. How can I make it more interesting and complicated? I'm going to add an obstacle to the problem. So what does it mean? It means that I have a surface, some surface that lies here in the space, and that my membrane is not allowed to cross it. So you can think the simplest case. Here I have this desk. I have my elastic membrane which bends. And if my wire is close enough, my membrane will touch this desk, and that is not allowed to pass through it. So let's add an obstacle. And in the simplest case, you can put as an obstacle just the plane, which will be like if this is my last variable. So this is my, let's say, this is the xm plus 1 variable. So this would be xm plus 1 equals 0. So I have this plane that acts as an obstacle. I have my metal wire, and my membrane bends. And then somewhere, this will touch the plane. So what am I doing? I'm just still minimizing the same energy here. But because of this obstacle, my function u, so u is my function that represents this surface, is not allowed to go below this plane, which means that u is non-negative. So I'm just going to add a constraint here, u non-negative. So this is called the obstacle problem now. You can do things a bit more complicated than this. So you can, instead of just taking a plane, you will take some smooth surface. But let's take a plane for simplicity. OK, so what do you do now? When you have a problem like this, the first thing you ask yourself is, for such a mathematical problem, is there existence of solutions? Is there uniqueness of solutions? And the answer is yes. This is a nice convex problem. But then if you want to study it, you need to write down some equations. So the first thing you want to do is to write down a PD for this problem. So writing a PD for this problem is not totally trivial, although it's not too complicated either, but it's not totally trivial. So the way you do is what you do. You take a minimizer, and then you start to perturb it, first variation analysis. You do first order, so Euler-Lagrange equations. And you try to write the criticality conditions for this. With a bit of work, you can prove, so if you use a minimizer, then you solve a PD. So this Dirichlet part of the energy will give you a Laplacian. And then you have the potential part of the energy, which will give a source term. But you have to take care of the fact of this constraint. And it will give you a nonlinear PD, which is the following: characteristic of U positive. So characteristic function of a set A is the function which is 1 if x is in A, and 0 if x is not in A. So here it means the following. Maybe I will draw the picture again. It's easier. This means that I have my function, let's say, my u. So this is my u. And what happens is the following. So where u doesn't touch the obstacle, so here, at these points, the Laplacian of u is equal to 1, because this function will be 1 everywhere where you don't touch. Where u is 0, well, u is 0. But then what happens here at the free boundary, at this boundary? So at this boundary, there is hidden a condition which comes from the fact that this function, this right-hand side, the characteristic function, is bounded, is a bounded function, is always L infinity. So because it takes values 0 and 1. So because the Laplacian is bounded, it implies that u is C1, is continuously differentiable. And so if I have a non-negative function which is continuously differentiable, at these points, not only u is 0, but also the gradient of u is 0 by smoothness. Which means that on this boundary, u satisfies both a Dirichlet type condition, u vanishes, but also a Neumann type condition, the gradient of u vanishes. So I have both 0 value and 0 flux, which is a non-determined boundary condition, because usually you cannot prescribe both. But here, in some sense, you can, because this is what is going to govern the geometry of this free boundary. So this is the picture. So you have a function which is 0, gradient 0 where it vanishes, and then it goes up, and it goes up with Laplacian 1. And the question is, what can I say about this function? So this problem comes from elasticity, but actually, just as a side remark, so I decided to focus the talk on this because it's also easier to explain, but a remark that if you add time, and you consider dtu minus Laplacian u equal minus characteristic of u positive, this corresponds to the so-called one-phase Stefan problem. And the Stefan problem, in this model, dTu corresponds to the temperature of water. And what this this region represents, this U positive represents the region where there is water. So U positive is the water region, water. And U equals 0 is the region where there is ice. And then what here is happening is that ice is melting. And so this is modeling the melting of ice inside water. So these kind of free boundary problems are very rich class. And in some sense, the effect of, mathematically, they can, there are a lot of similarities between this parabolic case and this elliptic case. So let's say that this studying that problem is also actually very nice implications. Yeah.
Is dTu or U?
The dTu. Yeah, so the temperature is not C1, it creates angles. So the temperature looks more like this in the ice. So you have the ice. Let's say this is the one phase. So the ice is at 0 temperature. So the ice is theta equals 0. And then you have the temperature of the water, which is theta positive. This will always come with an angle. And the speed at which the ice melts is proportional to the gradient of the temperature of the free boundary. But then if you integrate the temperature in time, so you take the primitive, you define U, and this becomes the obstacle problem. So there is a nice connection that has been discovered in the 70s between the one-phase Stefan and the obstacle problem. But anyhow, it's not important for my talk. I just wanted to mention that this kind of problems is actually, let's say, it comes from elasticity, this one. But actually, there are also many other settings where this kind of PDE arise. So what do you want to do in this kind of problems? You have a PDE where you have a function and a boundary. This what we call the free boundary, which is the boundary of the region where U vanishes. And so the questions that we want to understand. So first question is, what can we say about U? And second question, what can we say about the free boundary, which is the boundary of U positive? So we want to understand both the function and its free boundary. So about the function U, you can observe that the Laplacian of U is bounded. I noticed that. But also the Laplacian of U is not a continuous function because it jumps, right? So where U is 0, the Laplacian is 0. Where U is positive, the Laplacian is 1. So there is a discontinuity. So it's not a continuous function, which implies that U is not twice differentiable. It's not C2. So second derivatives are discontinuous. So how much regularity can you expect? Well, this was already proved in the 60s, 1962, I think, the first time by Frese. U is C11. So the gradient, so I already told you that U is C1. So U is C1, and gradient of U is Lipschitz. Or let's put it in the way, the Hessian of U is bounded. There are many ways of writing it. Okay, so the second derivative exists almost everywhere, and they're bounded functions, which is the best you can hope because the Hessian cannot be continuous. So just before, it's just bounded. So this is about the solution. So this is very well understood. The real question is, what about the free boundary? This is really the challenge. So the study of free boundaries, this kind of PDEs, started again in the 1960s. But let's say it took some time to kind of develop a robust theory for this kind of objects. And so here I would like to start to mention a couple of results. So here the first important result is due to Kinderlehrer and Nirenberg. 77, where they proved the following kind of result. They proved the following. If, so these are conditional result. Let's say that I have a ball, BR, and I know that inside this ball, so I have my free boundary. So this is my boundary of U positive. Here on this side, U is 0. And on this side, U is positive, right? And this surface here, this is a C1 surface. Okay? So you assume already that you have a very nice C1 surface that separates the region where the obstacle touches from the region where it doesn't touch. Then the surface is infinity. So if you are at least C1, then in fact you're much smoother. This is in PD what we call kind of bootstrap regularity theory. You can think of it in terms of Schauder estimates for elliptic PDs. So once you have a bit of regularity, you can keep going, and you can go actually as much as you want. In fact, you could go all the way to analyticity here. So the key point here is a sort of conditional results. It tells you once I have a nice situation, where nice means this really nice separation U0, U positive with a nice hypersurface, at least C1, then I can go all the way on. So this is what they proved. The only, let's say, catch here is that it is a conditional result, if, then. But then the question is, when does the if is satisfied, right? So let's say, luckily for us, there was a young mathematician at the time who started to work in that problem and gave us a beautiful insight. So again, this was same period, and this is Caffarelli in 77 again. What he proved is I would say one of the most fundamental results in the whole theory, which kind of opened the way we now understand free boundaries. And what Luis did was the following. So he proved the following theorem. He proved that the free boundary can be decomposed, is made of two parts, a regular part union a singular part. Okay? The regular part is all points where Kinder-Nirenberg applies. So you have a chunk of the free boundary where you can apply this theorem. And then you have another set, singular points. And what are the singular points? The singular points are points where the following happens. If I take a point here singular, for every ball around it, so I take the point x, let's say, and I take a radius r. And so what I can do is that I can find a plane, so some direction E on the sphere, Sn minus 1, such that the free boundary, it's all inside this narrow strip. And this strip, it's a little over. So it's much smaller than R. So what he's telling me is that singular points are points where when I look at my free boundary, all the free boundary is extremely close to a hyperplane around that point. And this is true for every scale R. So, and there is nothing else. That's the strength of the theorem. So let me try to give you an example which I think explains this. In the yeah.
You mean not just the free boundaries in the strip, but the whole zero set?
Right. The zero set will be then in the strip. Well, once the free boundary is there, then okay, yeah, I see what you mean. No. The zero set is in the strip. Absolutely. Sorry. Yeah, U equals 0 is all here. Yeah, you have the half situation. So let me try to explain this with a picture. Think of this. So this is my function is defined in the plane. So this is the omega plane, the omega region. So I have to tell you where is U0. So u equals 0 will be all this. So u equals 0 is here, u equals 0 is here, u equals 0 is there, and everywhere else u is positive. Okay? So this is my free boundary. It's made of 2 drops and a line connecting them. If you take any point here on this drop, except at the tip, you take a ball around it, and you see here u is 0, here u is positive. This is a nice surface separating. I mean, this situation, this curve has to be infinity by Kinderler and Nirenberg. Instead, if I am at any point here, you see that if I take any ball around, my 0 set is this part, this small cusp, plus a segment. And this is infinitesimally closer to this line. Okay? So, for instance, what Caffarelli tells us is that this picture is not allowed. You cannot reach this with an angle, right? So this is forbidden by this, because this theorem tells you that you have to asymptotically converge to a plane, let's say, to a half plane, to a hyperplane, or to a segment in 1 dimension. So this is not allowed, for instance, by Caffarelli. So this is one picture, which looks very nice, but just to tell you that things are more complicated than just, a segment with a drop, you can actually build solutions. Okay, here I will be cheating a bit because I took as an obstacle, you see the hyperplane, xn plus 1 equals 0. And then some things are not allowed for that hyperplane because the hyperplane is analytic. But let's say if the obstacle was infinity, I will do everything I want. So there is always a big difference between analyticity and infinity regularity. But let's say modulo small details. Let me build a second example, which is also enlightening, I think. So take a segment and start to do the following. You take a segment, you remove 1/3 of it. You remove 1/3 of it in the middle. And then you keep doing this, right? So this is the construction of a Cantor set. And then what you do in this part that you removed, you add something which looks like, I don't know, a leaf with 2 cusps in the end. And then this, I do the same. So here is a cusp, here is a cusp. So 2 smooth curves that end with a cusp. And you keep doing this. If you do this, you will get, so this is so u will be positive here, and these sets represent u equals 0. So all points here are regular, and all points at the boundary of these leaves are singular. So here the singular set is the usual Cantor 1/3 set. So you can you can make this construction playing with that dyadic, and then you can show that the singular set is actually a Cantor set. And you can play with these kind of constructions. So just to say, you see, the picture is not so easy, right? So you have a region which is the regular part. That's why actually we call singular, because it can be ugly. So there is a regular part where you have a kind of a PD theory kicks in and tells you that things are much nicer than you expect. Or let's say much nicer than one may expect, right? The PD is not even regular by itself. And then you have these points, the singular points, where everything seems to fail because they can be, you see, totally disconnected. It's just a closed set a priori. So this looks a bit, I don't know, deceptive, and motivates 3 questions. So now I'm going to focus only on the singular set, right? So I told you I wanted to study the free boundary, but I told you, okay, the free boundary is made of regular and singular points. Regular points we understand. Let's focus on singular. So question 1. How smooth, whatever this means, is the singular set. Question 2. Let's look at that picture. Let's think of theorems in geometric measure theory. So usually when you have rough objects, what mathematicians like to prove is to say at least that the set of points where things go wrong is small. So in minimal surface theory, there are very classical theorems that tells you if I take a minimal surface, then this minimal surface is going to be smooth up to dimension 7. And then from dimension 8, there is a counterexample, which is the Simon's cone, Jim Simon's cone, right? Which is a singular minimal surface in dimension 8. And then building on this, you can prove that the singular set is much smaller than the surface itself. So this is the kind of theorems people like, right? To say, at least to say, okay, things go wrong, but the place where it goes wrong, it's very, very small. Here, things go actually in a bad direction, because in this example, the singular set is a segment. The regular set is two smooth curves, and they're both one-dimensional objects. And they are one as big as the other in some sense, right? I mean, they have the same kind of size. So, is it common that reg and sing have the same size? Like in that picture. And then there is a third question, which is a bit more, so the motivation for it looks is a bit technical, so I will not explain to you why I want to study it. People who are familiar with GMT, they will see it immediately, why it's important. But I want to mention this because it's actually connected to another problem, which I think is beautiful. So the third question is that, can we understand all global solutions of Laplacian U equal characteristic of U positive? So my problem is currently has been defined in some domain omega, okay? But usually in geometric measure theory, in many problems, what we do to analyze solutions is to do blow-up procedures, which means that you take a point, you start to zoom in, and you try to, and you rescale. And as you do this procedure, you naturally end up with functions which are defined in Wall Rn. So a global solution means a function U defined on the Wall Rn, which satisfies this PD everywhere in Rn. And we want to classify them. These are called like Liouville type theorems, okay? When you classify global solutions. So this is important for the free boundary as well. I will not not say more, but let's say this is the third question. Okay, so we have 1, 2, and 3. So let's start with 1. And you will see that 1 is actually related to 2. And then I will move to 3. If you have any questions so far before I start this, you're welcome to ask.
Would you have to have a very unusual obstacle to produce some of these examples?
Do I need an unusual obstacle to produce this? No. So, I mean, depends what it means unusual, right? So I will come a bit to this point. Is it common? But let's say if you give me the obstacle, once you give me the contact region, I can build a infinity obstacle for which this is true. But maybe the definition of unusual has to be defined, but this will probably be connected to my point 2, which I will discuss in a few minutes. But the bottom line here is that these examples exist. So that's the, so we cannot do much about that. Osmoticing. So let's discuss 1. The first theorem in this direction comes, again, from Caffarelli. So in 1998, he proved that the singular set is contained in a C1 hypersurface. So you remember my example. I had two examples. Probably I should have kept them, but OK. One, it's easy to redo, and the other. Well, in this case, the singular set is a segment. Segment is contained in a very smooth hypersurface, a line. The other example was this kind of Cantor set. OK, so I had this Cantor set here. But again, this Cantor set is a Cantor set, but it's contained again in a line in my example. So a line is C1. So you cannot prove that the singular set is smooth, but at least you can prove that it's containing something nice. That was the kind of first result by Lewis. So people have tried for a few years kind of understanding how to push this result. Can you push higher this C1? Can you go to C infinity, C2, C3, C10, C infinity? And I will say that I don't know. There were partial results in 2 dimensions from Georg Weiss, but it wasn't very clear how to push it to higher dimension. And then in 2019, together with Joaquim Serra, what we realized that actually we could prove something stronger. And it was the following, which I think was then which was for us really the beginning then of a new analysis. We proved that the singular set is contained in a C11 hypersurface. Think of C2 if you want. It doesn't matter here. I mean, we could have proved probably C2. But what is important is not just this. There was an up to a codimension 3 set. So what we realized in 2019 with Joaquim is that the singular set, that Lewis result is actually optimal. Unless you take your singular set and you throw away some bad points, which are very singular within the singular set, you cannot push this regularity further. So these points start to exist in 3 dimensions. So in 3 dimensions, you can build new points that we call anomalous, because we couldn't call them singular anymore, because singular points already existed, so we said anomalous. So there are these anomalous points which have codimension 3, and if you throw them away, then you can prove more regularity. And this goes a bit in the spirit of minimal surface theory, right? At least you have now a set which is uglier inside a singular set, and if you throw that away, you get more regularity. And then to Rn. No, it's codimension 2 in the boundary, codimension 3 in the space. So they are points in dimension 3. So this was the beginning, and then after that, 2 PhD students, Franceschini and Zaton, in 22, they actually proved that singular set. So they were both students in Zurich, and the singular set is contained as infinity hypersurface up to a codimension 2 set. So actually, you have to give up a bit if you want to go to C infinity. There are some bad points. I mean, you can push regularity higher than C11, but you will get stuck at some exponent, which is like C5 over 2.5, unless you throw away more. So there are some points, but in reality, if you really want all the way to infinity, you have to remove a codimension 2 set. So in the plane, these points exist already. But still, it's 1 dimension less than the free boundary, at least. So the moral here is the following. The singular set is made of can be stratified in points which have different kind of regularity. And in a sense, all these points which are low regularity are low dimension. And then the bulk of the singular set is actually extremely smooth, in the sense that it's contained at least in a very smooth set. It's not smooth by itself because it can always be a Cantor set. But let's say there is at least a nice structure around it. You could think, OK, mathematicians, as usual, they want to prove strange theorems, right? Why should I care? Also, all this terminology. Maybe 2 will be a bit more convincing, because to prove 2, we need this 1. So 2 is is it common that singular set and regular set are, have the same size? In particular, you see from physics viewpoint, you will say, well, I never in nature will ever observe something like that. Or is it just some mathematician artifact that just built an example which I will never observe in my life, okay? So what's going on here? And this is what 2 is about. So in Scheffer, in 1974, made a conjecture. And the conjecture said, generically, the singular set should be empty. So he said, OK, perhaps you can build very ugly singular set, but the moment you perturb a bit your solution, there should be no singular set whatsoever. In fact, you never observe any of this. And all I see is always a nice, beautiful, analytic Capper surface that gives me my free boundary. So forget about this segment, forget about this cusp, forget about counter sets. This is what Scheffer said. He didn't really say what generically means. It was just a word at some moment in this paper. He was talking about other PDEs, and then he mentioned this for the obstacle problem, or for a more general class of PDEs, in fact, that includes the obstacle problem. But he was vague about generically. So now we have to decide ourselves what generic is. I can choose. So maybe let me keep this, just to keep you the 3 questions. And I want to formulate this in the following way. So I'm going to take, remember the setup, right? I have a domain omega, and I have some boundary conditions. Right? So I have omega, and I have my f, and then u on the boundary of omega is equal to f. So to talk about generically, I need to perturb my boundary condition in some way, right? So I'm going to consider a 1-parameter family f subscript t, t in minus 1, 1. So t is my parameter. And let me make it monotone for convenience. So dt ft is strictly positive. So it means that I have my boundary datum, and I move it up and down. Doesn't matter how you do it, but you move it monotonically. So this will give you a family of solutions, which are the membrane corresponding to each boundary data, which will also be monotone. So for each, let's say you have an f, this will give one solution. And then you take a second f, which is higher, and this will give a second solution above, and so on. So this corresponds to 2 different values. So this will be fs, and this will be ft. OK? So you have a family Laplacian ut equal characteristic of ut. So t is not the time here, it's the parameter. Ut is non-negative. And ut on the boundary is equal to ft. OK, then the theorem. And to prove this theorem, we need to all this kind of analysis of the singular set that I discussed before and more. So this is joint with Rossoton and Serra. This was done in 2020, I don't know, 2021 maybe, I don't remember. 2020 or 2021. And the theorem says that for almost every t, with respect to the Lebesgue measure, the singular set has singular set of ut as hn minus 4 out of measure 0. So it tells you that if you perturb the boundary datum generically, in fact, what you see all the time is the singular set has codimension 4. In particular, this implies that sing of ut is empty for dimension at most 4. So if you're in R2, R3, and R4, this is always empty. So the Scheffer conjecture is true. OK? For almost every t. Yeah, this is now my definition of genericity.
You don't have a uniform condition on the DTF.
No, just that it's strictly positive.
But you can
That's,
raise one side as
yeah, I can move.
the other.
Doesn't matter, in fact. The moment is a non-trivial, as long as I'm moving, that is not like fixed, so it's not the same thing. There is no uniformity. Actually, I don't even need to move everywhere on the free body. I can just move here and not move here. I just need something move somewhere. So I would say actually this is the strongest definition you can take of genericity, because then this is like a full measure condition, and actually the fact of being open, the fact of being empty is an open condition as well. So once it's empty, you are empty in a neighborhood. So it's an open dense set. So it goes both in the, let's say, measure theory sense and the kind of dynamical system sense. Is it sharp? So the PhD project of the student of myself and Joachim now is to put a 5 here.
What do you think?
I think that this method will stop at 5. I don't think with this method you can go further than that because of these anomalous points that are there. Actually, it's interesting. So after we did this, a couple of years later, there has been this paper by, oh my God, Chodos, Witt, Christos, yeah, Mantouridis. And then there was another sequel. Right, Schultz as well. Yeah, thank you. Where they proved that generically for minimal surfaces, if you perturb the minimal surface, then they will have no singularity in dimension 8, 9, and 10. Okay? You look at the proof, and it's very similar to this. Okay? It's really very similar, the approach and everything. And dimension 8 is where you have Simon's cone. This corresponds to dimension 1 here. Dimension 9 corresponds to dimension 2. Dimension 10 corresponds to dimension 3. So their result in dimension 10 corresponds to this theorem up to dimension 3. So when they told me about that, I told them, then you should be able to do dimension 11, because we did 4. So our 4 is their dimension 11. So I think they told me, oh, yeah, I think we can do it. I'm not sure they posted it already. At some moment, they mentioned me that they were able to do it. So I don't know if the preprint came out already. But at some point, they say, no, I think now we can do 11 as well. So, but you face the same difficulties. And I think there is a hope for 5. But the point is that here we are trying just to move with one parameter family of variations. And if you wanted to do more, you will have to find a way to construct variations, so multi-parameter family of variations that are linearly independent, whatever that means. No, there is no counterexample. This doesn't, I don't have any clear intuition. So what I think is that there could be something.
There is no like point where
No.
something like Simon's cone can say
No. No, at the moment it's still open. What I think is that this method could push it up to 5. That I can believe, although it's very hard. But where it will stop, I'm not sure. So let me try briefly to discuss point 3 before, still have a few minutes. Because I think it's interesting how this problem, all this obstacle problem, is connected to something very different. Again. So global solution. Let me try to do something a bit by hand, not very rigorous, but there is a way to make it rigorous. So let's say that I have a global solution. What does it mean? It means that I am in the world space and I have a region, which could be bounded or unbounded, where u is 0, okay? And here u is positive. Let me write the PD. Laplacian u equal characteristic of u positive, right? Let me give a name to this guy. So the characteristic of u positive is a function which is 0 here and 1 here. Call this rho. Rho by density of mass. So if you call this rho, this is a density of mass, which is 1 here in the complement and 0 here. What is Laplacian u equal rho is the nice Poisson equation. So u with this formulation, U is just the gravitational potential generated by rho. Okay, which means that minus grad U, or grad U, whatever sign, is the gravitational force. Okay, so I'm taking an infinite density, constant infinite density 1 in the complement, and then I look at the gradient of U, which is the gravitational force, and then I look at this region, U equals 0. So where U is 0, gradient of U is 0, which means that there is no gravitational force here. So having a global solution to the obstacle problem, it means that I can find a shape, this contact set, such that if I put constant density outside, I have no gravitational force inside. Now the question is, which shapes can do this? So the first example to this problem comes from in 1678, when Newton proved the no gravity in the shell theorem, that tells you that if you put constant density on a shell, on a spherical shell, there is no gravity inside. And then if you integrate shells, you get balls. So U equals 0, in Newton terms, this would say that U equals 0 can be a ball. So you can build global solution to the obstacle problem, which have 0, the 0 set is a ball, and then they're positive outside. If you go further, I checked this carefully this morning, in 1785, Laplace, and then there has been Ivory in 1809 Ivory, U equals 0 ellipsoid. So Ivory gave a more elementary proof of this fact that was already discovered by Laplace. And there have been a lot of similar contribution by many people at that time about these ellipsoidal shapes and which gravity they generated. But you can build solution to the obstacle problem which have an ellipsoid at 0 set and then they're positive outside. Now, if you take an ellipsoid and you center it, you make it pass through the origin. So you don't center the origin, but you make it pass through the origin, and then you zoom, you rescale it, and you take a limit, you can build a paraboloid. So U equals 0 can also be a paraboloid. So paraboloids are a generalization of a parabola, and every parabola is a limit of ellipsoids. Just take ellipsoid through the origin and make them bigger and bigger. So just by taking uniform limits of this, you build solutions of this. So you can have balls, you can have ellipsoids, you can have paraboloids. So let me denote E and P by ellipse and parabolas. And then you can artificially add dimensions always. So you can always take an ellipsoid in k dimension cross Rn minus k, or a paraboloid in k dimension cross Rn minus k. So you can always add fake dimensions, right? So these are the possible examples that Newton and Laplace and Ivory gave to us. And then the question you can ask is that, okay, these 3 smart people gave us these examples. Can someone else give us an extra example? So there have been quite some work, but I don't have much time. So I will summarize it quickly. So let's say there have been a bunch of works from 1931 until 1986, which proved, so, well, let me go quick. There has been Di Benedetto, Friedman, and many people, but let's say the conclusion is that if U equals 0 is bounded, like in my picture there, is a bounded set, then U equals 0 has to be an ellipsoid in every dimension. So they proved that if the contact set is bounded, it can only be an ellipsoid. There is nothing else. Then the question is, what about unbounded sets? So what the contact set is unbounded? So in 1981, Sakai proved that if n is equal to 2, then u equals 0 is either an ellipsoid, a paraboloid, or maybe a half space, but nothing else. So half space is just a trivial version of ellipsoid cross R. Or let's say intersection of two half spaces. But this was two-dimensional, and when you're in 2D, harmonic functions are very much linked to complex variables techniques. So in fact, this paper is about complex variables. So you cannot use complex variable techniques in higher dimension. So the question is, what can you do in general arbitrary dimension for unbounded sets? So in 2022, Eberl, Weiss, Shagolian, and Weiss proved that if n is greater or equal than 6, then you have only ellipsoid, paraboloids, and products. And I will explain what I mean by n greater or equal than 6. Well, n greater or equal than 6, what does it mean? It means that you have if you are in dimension at least 6, and your solution is not trivially a lower dimensional solution. So it's not like a 3-dimensional solution times fake variables. So if you have a real, at least 6-dimensional solution, then it must be of this form. And then in 2025, Eberl, myself, and Weiss, we proved that yes, also for n greater or equal than 3, which then, with the result of Sakai, closed the picture. So moral of the story, Newton and Laplace found them all back in 200 plus years ago, right? There was nothing else. And this concludes the picture. So this is, of course, classifying global solution to the obstacle problem has implication for the obstacle problem itself. But let's say I think it also was a nice problem by itself, right? Understanding this global classification. And finally, now it's done. And with this, I think also my talk is over. Thank you.